Hey everybody, so in this video I'll go over problems 5 through 8 from the review, and these are from section 3.7. And so we want to solve all of these optimization problems. And you'll notice that there are some included steps that you should include in your response, and these steps will also be listed for any optimization problems on the quiz. So step 1 is you should have a properly labeled diagram, and then it should have all of your variables on it somewhere so that we know what each variable stands for. We need a function that models the quantity to be optimized, so we need the optimization function. Number 3 says a reasonable domain for the independent variable. I don't mind, you don't have to write that down, but you should think about that. For example, if we're talking about um, the dimensions of an object, right? We shouldn't have any negative numbers in our dimensions. So you can just think that part in your head. You don't have to write it down. Step 4, correct use of calculus to find the max or the min. A reasonableness check against the domain, so make sure that the number that you get does make sense in the domain of your problem. And then a numerical answer, you should round to 3 decimal places if it's something that you are approximating using a calculator. Make sure you have proper units, and a complete sentence. I'm not going to write the sentence today just for the sake of time, but you would write like, uh, blah, blah, blah is a minimum because blah, 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 just like we did in the notes. So let's get started. So number 5, we've done a similar problem to this in the notes. Determine the points on y equals x squared plus 1 that are closest to 0, 2. So I'm going to do a sketch. And that's the function. Oops, no, it's not. Shift it up 1. Y equals x squared plus 1. So something like that. And then this would be the point 0, 2. And so the closest points x, y, we can see from symmetry that there should end up being 2. This is why the sketch is handy. So what do we have here? Well, the constraint is really the given equation, right? It has to satisfy this y equals x squared plus 1, so that's the constraint. And then the goal is to, if we're finding points that are closest, what we're doing is we're minimizing the distance. And so you're going to use the distance formula. And we want the distance between the point 0, 2 and the point x, y. So the distance formula is the square root of the difference of the x values squared plus the difference of the y values squared. And from here we can do a little bit of substitution. So first of all, x minus 0 squared is just x squared. And then I'm going to replace the y with my constraint, x squared plus 1. And so now we are ending up with this x squared plus the quantity x squared minus 1 squared. And then you can multiply that out, and you should end up with the distance is x to the fourth minus x squared plus 1. And so if we want to minimize the distance, we just want to minimize this. So we want to minimize this expression that's under the radical. You certainly could do it with the radical, but it's if you minimize the thing inside of the square root, then you are automatically minimizing the square root of that number. So to make it easier for the derivative, just minimize the inside. And so this is d, and so we need the derivative, d prime. And d prime of that is going to be 4x cubed minus 2x. That's it. And this is a polynomial, so to find our max and min, we're going to set that equal to 0 and factor. I'm going to factor out a 2x, and I will be left with a 2x squared minus 1. Set those equal to 0, and we get x is 0, and x is, that'll end up being plus or minus 1 over root 2. You can rationalize it or leave it like that. And so those are the critical numbers. And if you think about this, you want to think, sorry, getting distracted. You want to think about, are these reasonable in the domain? So does x equals 0 make sense, and would plus or minus 1 over root 2 make sense? And I think yes. So this, if x was 0, basically you would be saying that this point here is the one that's closest to the point 0, 2, or it might be somewhere over here or over here. So to check, we should test all of them. Sometimes you only end up with one number, but you should still always check them on your number line. So if you test the intervals here, you're going to get d prime is less than 0. Here you'll get d prime is greater than 0. Here you will get d prime is less than 0, and here it's going to be greater than 0. And so what were we looking for? We were looking to minimize the distance. We wanted to minimize it. So we want to know which of these three are a minimum. We know that a minimum happens when our function switches from decreasing to increasing. And so that's going to be here and here. These are both local min. Those are both local min. So those are the two x values. So here there are two different points that will minimize the distance. And again, that's because of the symmetry of this function. And so then you should also find the y values. And so what you should end up getting are these points. You should get positive 1 over root 2, common 3/2, and then you should get negative 1 over root 2, 3/2. And remember, you should include a sentence responding to the prompt. So you should basically write that in a complete sentence, and you should state how you know, because d prime switched from negative to positive. Okay, let's try another one. A farmer has 400 feet of fencing to make 3 adjacent and congruent rectangular pens. And so here you have a little drawing already. What dimensions, x and y, will maximize the total area? Okay, so we're already given the dimensions, x and y. So if this is my x, this is going to be my y. And the goal is to maximize the area. So we want to maximize the area, and the area is going to be x times y. And what will our constraint be here? Oopsies, constraint. So the constraint is that we have 400 feet of fencing, and we're making all 3 of these pens. So we need fencing here and here and here, and those are all going to be x, and then this whole top thing will be y. So the constraint is that we have 400 feet of fencing, and that needs to cover 4x plus 2y. Okay, so then from here, hopefully you know the process. You want to isolate one of those variables, x or y, and then substitute it into your optimization function. So I'm going to isolate the x. So we're going to get 400 minus 2y equals 4x, and then divide by 4. I'm going to divide each of these by 4. So 400 divided by 4 is 100. And 2y divided by 4 is going to become negative 1/2y. And now substitute that into this guy. So I'm going to change the x into that. Multiply by y, distribute, and then take the derivative. And we get 100 minus y, which is nice and easy. It's just a linear function, set it equal to 0. And we get y is 100. And so you should just confirm when you put this on a number line. 100, and let's see, think about again the domain here. Would it make sense for y to be any negative number? No, so it's kind of nice to like show that it would stop here at 0. Okay, and then you test, and in this region we get a prime is positive, and here a prime is negative. So we switch from increasing to decreasing, which means that 100 is indeed a maximum. And then use the constraint to find x. So y equals 100. And then that implies, remember, x is 100 minus 1/2 y. 100 minus half of 100, that's 100 minus 50, which is 50. And so the dimensions are 100 feet, don't forget the units, by 50 feet. And then you should support your answer with a sentence. Okay, 2 more. Determine the area of the largest rectangle that can be inscribed in a circle of radius 4. So these ones can be tricky, but once you see it once, it's not too bad. So what does this mean, first of all? Well, if you have a circle and you inscribe a rectangle, that means the rectangle's corners are lying on the circle. This is obviously not drawn very well. Now I'm going to draw in axes to just make this really clear, right? And our circle has a radius of 4, which means that this distance here is 4. And that point right there is going to be the point. So I like to think about this as the unit circle, just because like you're already familiar with that. But really putting the circle on the coordinate plane just helps you think about the equation. So if we call this the point xy, because where those intersect, right, this would be, let me get another color. It's going to be a colorful one. This would be our x, and then this would be our y, right? And so if you go over x up y, you get that point right there where the corner is touching the circle. And we know that this length is 4 because the radius is 4. So what does this tell us? Well, the constraint will be the equation of this circle. And the equation of a circle is x squared plus y squared equals r squared. And here r is 4, so r squared is 16. So that is the constraint. And then the goal is to determine the area of the largest rectangle. So we want to maximize the area. We want to maximize the area of this rectangle, which looks like a square right now, how I drew it. And so what is the area? Well, the area is not x times y, because what do you notice about x and y? The x is only half of the length of the rectangle. So this rectangle has side lengths of 2x and 2y. And so the area here is 2x times 2y, which is 4xy. So that's the setup of it. And then from here, same process for solving. So I'm going to do this part a little bit faster. So choose one variable to isolate in the constraint. I'm choosing y. And you're going to get y equals the square root of 16 minus x squared. It would be plus or minus, but I don't need the minus because y has to be a positive number. So I'm ignoring the minus. Now I'm going to substitute. And now we need to find the derivative. And so here we're going to have to use the product rule because we have 4x times the square root. I did not need the parentheses. We have the 4x, that's one sort of function, and then we have the square root of 16 minus x squared. So I'm going to bring this over here so I have space. I'm going to take the derivative. So product rule. So we have first function times the derivative of the second. And so for that, remember square roots to the 1/2 power, bring the 1/2 out front. We have 16 minus x squared to the negative 1/2, and then multiply by the derivative of the inside. So this is the chain rule, and that's going to be negative 2x. And then we need to add that to the second function times the derivative of the first. So the derivative of the first is going to be just 4, and then we'll have 16 minus x squared to the 1/2 power. Okay, and so let's see, then you want to simplify this as much as you can. And so we have, let's see, 4x times negative 2x would be negative 8x squared, but then times 1/2. So that's negative 4x squared. So we're going to get negative 4x squared. And then I'm going to move my square root of 16 minus x squared to the denominator. And then I have my plus 4 square root of 16 minus x squared. And so you can certainly make a common denominator here and do it that way. Or another way to think about this is we want to know where does this thing equal 0. We want to find the critical numbers. And so then you could just add the first fraction over. And then multiply both sides by 16 square root of 16 minus x squared, which is just going to undo the square root. Add the x squared. Oopsies, I have my 4 here. Get rid of the 4, divide both sides by 4. And so we get 2x squared equals 16. We get x squared equals 8. We get x equals plus or minus the square root of 8. Okay, so for critical numbers, we have wherever our function equals 0, also where it does not exist. So where does it not exist? Remember, that would be where this denominator equals 0. Excuse me, I have to cough. Maybe put down your volume. Sorry. Sorry. Okay, so this thing, so this is where the function does not exist. It's where this equals 0, which is where x squared equals 16, which is where x equals plus or minus 4. But think about this, you guys. Remember that the radius was 4. The radius was 4. And so, would this make sense in the context of the problem? Well, if the radius is 4, there's no way that the x or the y could be 4. They're going to have to be less than 4. because this whole thing is the radius. So the x and the y values have to be bigger than 0 and less than 4. So I don't need to include those. Only the plus or minus root 8. Actually, sorry, not the minus, only the positive root 8. So we've narrowed it down. We had lots of critical numbers, but really only one of them could be a possibility. Test it out on the number line. This should stop at 0. Square root of 8. Here a prime is going to be positive, and here it will be negative. And so it is indeed a max. And then you need to find the y value if you know the x value. Okay, but what was the question asking? The question was asking us to determine the area. It didn't say determine the dimensions, but we need to know the dimensions to find the area. So first, go to the constraint to find the y. So we have x squared plus y squared is 16. The x is square root 8. Square root 8 squared is 8. Subtract 8 from both sides, we get y squared equals 8. So y is also going to be the square root of 8. So both x and y are the square root of 8, but we were asked to find the area. And remember, our area formula was right here, 4xy. And so we have 4 root 8, root 8. Root 8 times root 8 is 8, and 8 times 4 is 32. And then you should put units, but here it doesn't tell us what the units are, so you can just write units squared. Okie dokie. Last but certainly not least, we have a closed box with a square base. So I automatically am thinking I'm going to want to draw this. Not very good artistically, as you can tell, but there we go. Okay, so it has a square base, which means that these need to be the same. But it doesn't say that the height is necessarily the same, so I'm going to give the height a different variable, y. Or you could call it h, probably makes more sense. Is to have a volume of 2,000 inches cubed. So that's giving you the constraint right there. The constraint is usually the thing with a number. So the volume, and volume in this case, right, volume is length times width times height, but in this case it's going to be x squared y. Because it's x times y. And this is saying that that needs to equal 2,000. That's the constraint. Now, what else? The material for the top and bottom of the cost of the box costs $5 per square inch, while the material for the sides costs $3 per square inch. So notice the units there, square inch, we're thinking area. Find the dimensions of the box that will lead to the minimum total. So we want to minimize the total cost. Minimize the total cost, which means we probably want to write an equation. Oh, also look, it's saying find the dimensions and what is the minimum cost. So pay attention to what the question is asking so that at the end you make sure you answer all parts. So in the end, we need to know the dimensions and the total cost. Okay, so the goal is to minimize the cost. Minimize cost. Oops. Okay, and how do we minimize cost? Well, we need a formula for the cost. So the cost is going to equal, so the top and the bottom cost $5 per square inch. So the top, which is here, costs $5 per square inch. And the area of that is going to be x squared because it's x times x, as will the bottom. So we have two of those. So we have 2x squareds, and they cost $5 each. In addition to that, we have the sides, the material for the sides costs $3 per square inch. So how many sides do we have? Well, this is the side, one of them. And we can see here that this area will be represented as x times y. And there's 4 of those. So we have 4 xy's, and those are costing $3 per square inch. So this is a formula for the cost. So let's make it look a little nicer. We can rewrite this as 10x squared plus 12xy. And then what do we need to do? Oh yeah, then we only want one variable. So I see that there's an x squared and an x, so I'm going to isolate the y up here. And that gives me y is 2,000 over x squared. We're going to substitute that in. Okay, and that gives us 10x squared plus, 12 times 2 is 24, so 24,000 over just x. And now that we've gotten that kind of as nice as we can differentiate. And so here we get 20x minus, remember, because this is really 24,000 x to the negative 1. So minus 24,000 over x squared is what that will become. Set it equal to 0. Set it equal to 0. And then we get 24,000 over x squared equals 20x. We get 24,000 equals 20x cubed. Divide both sides by 20. We get 1,200 equals x cubed. And so we're getting x is the cubed root of 1,200. Okay, so I know my x value now. This is the exact value, and then you can find the approximate using a calculator. And it looks like we're getting approximately 10.62. So you want to go 3 decimal places, 6265. On the AP, they don't care if you round up. So it's 6. So you can either what's called truncate it, so you could just like not write the 5, or you could round up. Either one is accepted. I'm going to round up. So there is my x value. Now I need to find my y value using my constraint. When you do this part, you should use the exact. So you should, when you like plug it into your calculator, you should use the exact. You should not use the rounded, because then you end up over rounding. So you shouldn't round within your problem. That's just my 2 cents. So we're going to have 2,000 divided by the cubed root of 1,200 squared. And it looks like we got 17. I'm not doing this on my calculator, I'm doing it on my computer, so hopefully it did it right. 17.711 for y. So those are the dimensions, and those are in inches. So the dimensions, and remember the dimensions, it's a box. So the dimensions are the x by the x by the y. So you should write all 3, even though 2 of them are the same. Okay, and then the final step is to write how much this would cost And oops, I skipped a step. Sorry, I'm just trying to make the video faster, but you should, when you find this number, you remember you should test it just to make sure. Um, and so for the cost, just plug it into the cost formula. I'm gonna let you do that. You should get 3,380 something. Okay, so plug it into the cost formula, plug in your x and your y values, and see what you get. All right, I hope that helps. If you have any questions, please come to the Sunday office hours at 11:30, or you could always email me as well, and I will see you in class. Bye.